Hey everyone, welcome back to my channel. Have you ever wondered how ChatGPT, Claude, and Gemini understand your text? There is a crucial step that happens before any language model processes your input, and that step is called as tokenization. Tokenization is used for writing better prompt, understanding your token limits and cost, optimizing your API usage, and debugging your model behavior. There are various types of tokenization: word tokenization, character level tokenization, subword tokenization, which is latest and recently used in latest model, and there is a byte-based tokenization. So LLM breaks down your input into tokens and then represent them numerically so that models can perform a mathematical operation on top of that. Now, why tokenization is required? As your simple text cannot be interpreted by the model, so that's the reason we convert simple plain English into the mathematical representation, and that is the first step of the tokenization. Tokenization is a process where we breaking word or text into smaller units called as tokens, and then language model can process it. So like I explained, there are four types of tokenization. In word tokenization, we consider each word as one token. Now here, problem is that when model is presented with some new word, model fills it with the unknown keyword, unknown predefined and unknown token. Now due to one of the new word, entire sentence meaning model can fail to understand. That problem is called as out of vocabulary problem. In order to solve that, engineers have come up with another approach that is called as character based tokenization, where each character can be considered as one token. Now here, since character is a token, there is a no unknown out of vocabulary problem has been observed over here. Any word you can decode into character tokens. Problem in the character tokenization is that for one word there can be five tokens. So let's say for hello there will be five tokens. So that way data has been huge and model has to perform a huge operations in order to train with that data or inference with that data. So that increases the power consumption and increases the number of tokens that has been consumed. And another problem over here is that character-based tokenization models fails to understand or need more effort to understand the contextual meaning. Contextual meaning means that a relationship between the words. So for the character-based tokenization, there is a lot of process we need to do so that model can interpret what kind of relation or what kind of meaning that word or the next word means for it. Then new latest concept which is currently used in most of the models is a subword based tokenization method where each word is divided into some meaningful subwords. So that way a problem which in character tokenization we have seen that a huge data has been submitted to the or propagated to the model. Instead of over here, due to subword based tokenization, the vector number of vector has been reduced, and any new word can be divided into meaningful subwords, and that way your token count can be reduced. Okay, then there is a byte based tokenization where each byte is considered as one token. You can go through the theory of that word level tokenization, character level tokenization, and subword based tokenization. Subword based tokenization, there are some examples like byte pair coding, which is used in the GPT model. There is a word pace, which is used in BERT model, or you can call it as Google Gemini model, and there is Unigram, which is used by T5 model. We'll look into a practical of these three examples. So there is this tool online available which explains tokenizer and token counter. You can choose a model which you want to use, you want to see, you want to practice on. You can provide your text over here and this tool will show a tokenized text. So I'll put hello, how are you doing? I am at railway station. So now here if you see, each different color represents one token. Okay? And if you see over here, railway station word has been divided into two subwords. Similarly, if you see bank robbery and river bank. Okay? You see over here, bank robbery. Like that way, for one word, there has been three tokens has been generated. For river bank, this word, there are two tokens have been generated. So this bank is a common across. You see a token ID. These are the numerical representation of each token. Okay. If you see over here, 17289 is for Riverbank Bank and 17289 is for Bank Robberies Bank. Okay. So this is three tokens for bank robbery. These two tokens are for River Bank, and this 198 is the new line operator. Okay. So that way, subword-based tokenization divides a big word into some meaningful subwords and then assigns each token to it, so that if new word is represented, it can still understand subwords, and based on that it can find out the contextual meaning in it. There are some statistics over here. You can go through it and practice out your prompts and see how many tokens you can use in your prompt. So I will switch back to the practical that we wanted to do. Okay, this what you are seeing is a transformer explainer. If you are not knowing a transformer, we will cover it in our next session. But transformer is the basic component of any LLM, and I'll explain where tokenization is used over here. This transformer basically predicts what will be the next word, so you can prompt it with the data visualization, empowers users to, and it outputs easily. Okay. Now, if you look where tokenization is there, I told you that it will be the first layer of any LLM. So your tokenization happens over here. Your input prompt has been divided into subwords, data visualization, empower word is divided into two words, two tokens, empower, and then users and two. So this is my input prompt divided into token, and then there is a token embedding that happens. So you see each token has been assigned with one ID. We'll look into embedding in our next session. Visualization has been assigned with 320704 tokens. So these tokens come from JSON-based vocabulary where each subword or a unique word is represented in one number. So from that number you can get token ID. So that is what tokenization is being used for. For the embedding, we'll look into next session. Here we are using a tokenizer example. We are using three models, GPT-2, BERT and T5. We'll iterate through the model and see how this input is tokenized. So our input is hello people, welcome to liberalization, and it will be tokenized with these three models. Okay. The output is ready. So let's see how GPT-2 BP has been tokenized or token. So hello, you see before people there is some unique word is there, unique character is there. Before welcome also there is some unique character. To liberalization. So for each new word, BP2 uses a G. So that represents that there is no connection or there is a space ahead. If you see for liberalization, it is divided into three tokens, libs, rel, lization. But for rel and lization, there is no unique representation. For BERT2, if you see, BERT2 uses a double hash for subword. So BERT2 has divided this liberalization in different way. It has a libre and then lization. But here BERT2 uses double hash before a token, so that tells that there is some word before. But there is a relationship between this word and word ahead of it. Okay. Similarly, for the T5 unigram, it uses underscore for the space. Okay, and it has also divided liberalization into different ways. Okay, so that way each tokenization model can tokenize your input statement differently. Let me take you through this example of character level tokenization. Here every character is considered as a token. This is useful in character level language models for certain low resource based languages. So input text is the hello NLP, and then we'll try to convert into character based tokenization. So our character based tokenization, as I explained, each character is considered as one token. There are 10 tokens we have. Our vocabulary has been created from that is 9 tokens, and index has been assigned. So that way, whatever token ID you were seeing, that are these. So for space, we have assigned token ID 0. For exclamation mark, we have assigned token ID 1. For H, it is 2. L, it is 3. So this is an incremental integer number. So this is our vocabulary. This is our tokenization. Okay. So in this, our token and its respective token ID has been assigned over here. And our encoded format will be 26778043521. So this each number represents a token ID. So if you see 2 is for H, 6 is for E, that way our entire text has been represented as an encoded tokenized token. I have another example which analyzes the token frequency. Corpus is nothing but a large data set on which LLMs are getting trained. We have chosen a small corpus over here to show an example. And when you run this example, you will see that your vocabulary will show you up like this. Your language has been repeated 5 times, so that way you can analyze your frequency of the tokens in this with this example. Feel free to try out this such examples and let me know in the comment box how you feel about it and what improvements you need in this. So we know that now LLMs cannot read words; they read numbers. But how do we get from a sequence of sentence to the list of mathematical identifiers? This infographic breaks down the pipeline perfectly. As you see, the input sentence is unhappily the fox ran. So first we start with our raw input. It looks normal to us, but the machine needs it broken up into standardized units. That's our step 2, the token chunk. But you notice that we don't just split into spaces. Look at unhappily. The modern tokenizers use a subword-based tokenization method. They break rare words into common building blocks or subwords like unhappy. It also separates the crucial symbols like commas, quotes. Each of these unique pieces is a token. Now we do get from Lee a number. This is a crucial part, the vocabulary lookup. This is a huge index table, often stored as JSON file. Like this snippet here, the tokenizer looks at every token we just generated and finds its exact match in the database. Every token in JSON list has a fixed numerical ID assigned to it. This is known as a token ID. Once every chunk is matched against the master's list, we generate step 3, the numerical IDs. This finalized list of integers is what AI is actually reading when it processes the word unhappy. It is a very specific code that is efficient for the computers to process.